In this lecture, we'll study about different methods of proof. So first of all, what is a proof? So proof of mathematical statement consists of sequence of statements, each statement being justified with a definition or an axiom or a proposition that is previously established by the method of deduction using only the allowed logical rules. Okay, so whenever you prove any statement, any mathematical statement, then that proof consists of a sequence of statements, and those sequence of statements are already being proved, or it may be an axiom or a proposition that is previously established. Okay, so there are two ways of proving proposition, directly or indirectly, and the proofs obtained are called direct proof and indirect proof, and further each has three different ways of proving. So basically there are two ways of proving a mathematical statement. One is called as the direct proof and the another one is called as the indirect proof. Okay, and this direct proof consists of three different ways, as well as the indirect proofs also consist of three different ways of proving a mathematical statement. So come to first the direct proof. So it is the proof of proposition in which we directly start the proof with what is given in the proposition. So in direct proof, whatever given in the proposition, will start with that and go step by step and we prove that one. Okay, so we know that in direct proof there are three different ways to prove a mathematical statement, and the first way is straightforward approach. So it is a chain of arguments which leads directly from what is given or assumed with the help of axioms, definitions, or already proved theorems to what is to be proved using rules of logic. Okay, so straightforward approach. In straightforward approach, to prove a mathematical statement, we have a chain of arguments. Means if we first of all we have an argument, then we from that particular argument we deduce or we come to another argument, and in this way we finally we approach to the mathematical statement that is to be proved. Okay, so come to an example here. So that if x square minus 5x plus 6 is equal to 0, then x is equal to 3 or x is equal to 2. Okay, now we have to prove this one by using straightforward approach, and this is one part of the direct proof. Okay, so this is the mathematical statement that is given, and we have to prove this x is equal to 3 or x is equal to 2. So we'll start with this x square minus 5x plus 6 is equal to 0. Okay, so which implies this minus 5x can be written as minus 3x minus 2x plus 6 is equal to 0. Okay, which implies we can take common here. In the first two terms, x can be taken as common, so x minus 3. In the next two terms, minus 2 can be taken as common. Okay, now this it can be written as x minus 2 x minus 3 is equal to 0. Okay, so this particular mathematical statement can be written as x minus 2 into x minus 3 is equal to 0 because both are equivalent. Okay, now which implies x minus 2 is equal to 0 or x minus 5 is equal to 0. So we know that if a be equal to 0, then a is equal to 0 or b is equal to 0. Okay, so from that we deduce this one, that if x minus 2 into x minus 3 is equal to 0, then x minus 2 is equal to 0 or x minus 5 is equal to x minus 3 is equal to 0. Okay, now so it can be written as x minus 2 plus 2 is equal to 0 plus 2, or x minus 3 plus 3 is equal to 0 plus 3. So it means if a is equal to b, then if we add any quantity on the both side, then the both side will be equal. So that is for a plus c is equal to, then a plus c is equal to a plus b, sorry, b plus c. Okay, so what is the meaning of this? If you add any quantity to the both side, then the both side will be remain same. So that is the meaning of this, which implies x plus 0 is equal to 0 plus 2, or this is x plus 0 is equal to 0 plus 3. Okay, so what is the meaning of this? Here 0 is the identity, okay, of the set of integers. Okay, so when we add a number, okay, with its inverse, then we get the identity number. Okay, so we can say minus a is the additive inverse of a. Okay, that is minus a plus a is equal to 0. Okay, so here 0 is the identity of this set of integers. Okay, it means if a is an element and we add that element with the inverse of that particular element, then we will get the identity element. So here the inverse of 2 is minus 2. So 2 plus minus 2 is equal to 0, where 0 is the identity element. Similarly here minus 3 plus 0, minus 3 plus 3 is equal to 0. Okay, which implies, so this is x plus 0 is equal to x, 0 plus 2 is equal to 2, or x plus 0 is equal to 0, x plus 3 is equal to 3. So here, since 0 is the identity of set of integers, then we can have a plus 0 is equal to a. Okay, so similarly here, so x plus 0 is equal to x, 0 plus 2 is equal to 2, x plus 0 is equal to x. Okay, so we got x is equal to 2 or x is equal to 3, so hence proved. So in this way we can prove that if x square minus 5x plus 6 is equal to 0, then x is equal to 3 or x is equal to 2. So come to example 2. Prove that the function f from R to R, okay, where R is the domain and R is the range here, defined by fx is equal to x plus 1 is 1 1. So it is a 1 1 function. Okay, so by the definition of a 1 1 function, it says that if fx1 is equal to fx2, then x1 is equal to x2. Okay, so this is the by the definition of 1 1 function. Okay, so if fx1 is equal to fx2, then x1 is equal to x2. This is the definition of the 1 1 function. Okay, now you have to prove this. Okay, so you have to start from this statement, if x1 is equal to fx2, then you have to prove x1 is equal to x2. Okay, so we can say that fx is equal to x plus 5 is a 1 1 function. Okay, so fx1 is equal to fx2, which implies function is this one 2x plus 5, so it can be 2x1 plus 5 is equal to 2x2 plus 5. This implies 2x1 plus 5 minus 5 is equal to 2x2 plus 5 minus 5. This is similar as if a is equal to b. Okay, if a is equal to b, then a minus c is equal to b minus c. It can be. Okay, now 2x1 plus 0, 2x2 plus 0. So this is nothing but by the definition of identity element. Okay, so where 0 is the identity element of this set of rational numbers R. Sorry, set of real numbers R. Okay, so it can be written as 2x1 plus 0 is 2x1 is equal to 2x2. So it is nothing but since 0 is the identity element, we can have a plus 0 is equal to 0 plus a is equal to a. Okay, now we can have 2x1 divided by 2. Now we'll divide the same quantity in both the sides. Okay, if you divide the same quantity on the both left hand side and the right hand side, then the left hand side is always equal to the right hand side. So if a is equal to b, okay, then a divided by c is equal to b divided by c, where c not equal to 0. Okay, so when we divide this one, we get x2, sorry, this one be x1 is equal to x2. Okay, so from fx1 is equal to fx2, we got x1 is equal to x2, hence f r is 1 function. Okay, so now come to the next way. Second type of proof, direct proof, is called as mathematical induction. So mathematical induction is a strategy of proving a proposition which is deductive in nature. The whole basis of proof of this method depends on the following axioms. Okay, so here for a given subset S of n, so here S is nothing but the subset of natural number n, set of natural number. The natural number 1 belong to S. Okay, so here natural number 1 is belong to S. The natural number k plus 1 belong to S whenever k belongs to S. Okay, so let's suppose the natural number k belong to belong to S. Okay, then the natural number k plus 1 belong to S. Okay, because if k is a natural number, if you increment that k by 1 and that particular value is also a natural number, let's suppose you take k is equal to 100, then we increment 100 by 1, then we get 101, and 101 is also a natural number. So in this way we go on increasing the value of k by 1 and on and so on. Then we come to a conclusion that the subset S is equal to the set of natural number n. S will be equal to n. Okay, so here, so according to the principle of mathematical induction, if a statement Sn is true for n is equal to 1, okay, so if Sn is true, statement Sn is true for n is equal to 1, okay, where n is a natural number, or for some starting point j. So instead of n is equal to 1, we can take any other value, any starting value j, and if Sn is true for n is equal to k, implies that Sn is true for n is equal to k plus 1. Then the statement is true for any positive integer n for all n greater than or equal to j. So in the mathematical induction, what happened? First of all, we will check whether this Sn is true for n is equal to 1 or any starting point j. Here we can take n is equal to 1 or we can take n is equal to 2 and so on. Okay, if it is true, then we check. Then we assume that Sn is true for n is equal to k. Then we prove that Sn is true for n is equal to k plus 1. Then the statement is true for all positive integers n, because here in the second point we got this, because in the second point we got this particular sentence here, because if k is a natural number and if k belongs to s, then k plus 1 belongs to s, because if you increment 1 to k, then you get k plus 1, that also belongs to s. So in this way, if you go on, then we get s is equal to n. So in the mathematical induction, first of all we prove Sn is equal to true for n is equal to 1 or any starting point value, and we assume that Sn is true for n is equal to k. Then you have to prove that Sn is true for n is equal to k plus 1, which automatically proves that the statement is true for any positive integer n for all n greater than or equal to j. Okay, so here, so you have to keep it in mind what is the starting point here. The starting point may be 1, starting point may be 2. It depends upon what to be proved. Okay, so come to one example here. So that 1 plus 2 square plus 2 to the power 3 plus and so on up to 2 to the power n is equal to 2 to the power n plus 1 minus 1 by mathematical induction. Okay, so here, so we can write it down Pn. So this can be written down Pn is nothing but 1 plus 2 plus 2 square plus 2 cube plus and so on 2 to the power n is equal to 2 to the power n plus 1 and so on. Okay, so here it can be written as, so this Pn can be written as, or Pn can be written as 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2 and so on minus 1. So here the value of n is starting from 0, 1, 2 and so on. Okay, so here now to prove this one, so let n is equal to 0. Okay, so when you take n is equal to 0, left hand side is equal to, put the value of n here 0, so left hand side is nothing but 2 to the power 0 is equal to 1. Okay, what is the right hand side? Right hand side is equal to 2 to the power, put here n is equal to 0 plus 1 minus 1. Okay, this is equal to 2 to the power 1 minus 1 is equal to 2 minus 1 is equal to 2, sorry, is equal to 1. Okay, so left hand side is equal to right hand side. Okay, hence P1 is true. There is the initial value or the starting point. So now let Pk is true. Okay, Pk is true, then we can have Pk is 1 plus 2 plus 2 plus 2 square plus 2 cube plus so on up to 2 to the power k is equal to 2 to the power k plus 1 minus 1. Okay, so let it be equation 1. Okay, now we have to prove now we have to prove Pk plus 1 is true, and you have to prove this one. So Pk plus 1 is nothing but 1 plus 2 plus 2 square plus 2 cube and so on to 2 to the power k plus 1. Right hand side is 2 to the power minus 1. So instead of n, put here k plus 1. So this is 2 to the power k plus 1 plus 1 minus 1. Okay, so this is the left hand side, this is the right hand side. Okay, so now I have to prove, let us, left hand side is equal to 1 plus 2 plus 2 square plus 2q plus and so on 2 to the power k plus 1. Okay, so it can be written as 1 plus 2 plus 2 square plus 2q plus 2 to the power k plus 2 to the power k plus 1. This is the previous term of this 2 to the power k plus 1. Okay, so we already have the value of this. Okay, so 1 plus 2 plus 2 square plus 2 to the power 3, it is nothing but 2 to the power k plus 1. Okay, so let me write it down here. So this is equal to, we can have 2 to the power k plus 1 minus 1. This is the value of this 1 plus 2 up to 2 to the power k. This is nothing but 2 to the power k plus 1 minus 1 plus 2 to the power k plus 1. Okay, so it is from 1 we got this one. Okay, now here we get 2 to the power k plus 1 plus 2 to the power k plus 1 is nothing but 2 into 2 to the power k plus 1 minus 1. Okay, this is nothing but 2 to the power, so power will be added here, so this will be k plus 1 plus 1 minus 1. Okay, this is equal to right hand side, so this is the right hand side. Okay, so by mathematical, okay, so it can, left hand side is equal to right hand side, so last statement can write down like this: pk plus 1 is true. Hence by mathematical induction, Pn, okay, so Pn can be written as this in the bracket or in this, Pn is true. Okay, so it is proved. So in this way you can prove by using mathematical induction. Okay, so this much for today. Thank you.